Module 5, Trigonometry. Let theta be an angle. From any point on the angle, drop the perpendicular to the other side. Note that we now have a right triangle, ABC, with the right angle, ACB. The longest side of the triangle, AB, is called the hypotenuse. The side AC is called the adjacent side, because it's next to the angle. The side BC is called the opposite side, as it's the opposite side of angle theta. The following fractions, BC over AB, would be the opposite over the hypotenuse, AC over AB, which would be the adjacent over the hypotenuse, and BC over AC, which would be the opposite over the adjacent, depend on angle theta. But it does not depend on where the perpendicular is dropped. This is because if we dropped the perpendicular elsewhere on the line, it wouldn't matter. In this example, as we discussed in the last module, BC over EF equals AB over AE and also equals AC over AF. Consider the first pair of fractions. BC over EF equals AB over AE. By cross-multiplying, we have BC times AE equals EF times AB, and now we can divide out BC times AE divided by AE times AB equals EF times AB divided by AE times AB, and then after we simplify it by canceling, we get BC over AB equals EF over AE, which is the opposite over the hypotenuse. Long story short, we see that the fraction opposite over hypotenuse does not depend on at which point the angle we drop to the perpendicular. The fraction always comes out the same. Similarly, the fractions adjacent over hypotenuse and opposite over adjacent have a similar invariant. They're always the same regardless of where we drop the perpendicular line. We call the fraction opposite over hypotenuse the sine of the angle, and we denote it by sin of theta. We call the fraction adjacent over the hypotenuse the cosine of the angle, and denote it by cos theta. We call the fraction opposite over adjacent the tangent of the angle, and denote it by tan theta. This is how sines, cosines, and tangents of angles are computed. Suppose, for the sake of an example, that we wish to find the sine of 40 degrees. We would first draw a 40-degree angle and then drop a perpendicular at any point. As we just discussed, it doesn't matter where. Then we measure the lengths of each of the three sides of the right triangle. In this example, first of all, notice that 1.38 squared plus 1.15 squared equals 1.80 squared, as expected by the Pythagorean theorem, which we discussed back in Module 3. Well, not quite. If you actually multiplied it out, you'd see the left-hand side computes to approximately 3.23, while the right-hand side computes to 3.24. This is a result of the fact that when we measure, we don't get the exact measurement. We only get approximate measurements. Now that we have the sides of the triangle, we can say that the sine of 40 degrees equals 1.15 divided by 1.8, which is about 0.64. The cosine of 40 degrees equals 1.38 divided by 1.8, which is approximately 0.77. And the tangent of 40 degrees is 1.15 divided by 1.38, which is 0.83. If we check these numbers in a calculator, we can see that our numbers are about right. The more accurate you are with measuring the segments, the more accurate these sorts of fractions will compute. Calculators very often have nice features that can perform these calculations for us, so that we don't need to draw any triangles by hand and compute these fractions. If we know one angle of a right triangle, and a length of any side, we can find the lengths of any other side using these formulas. Consider these examples. The first one, we've got a hypotenuse of 20 and an angle of 35 degrees, and in the second we've got an angle of 20 degrees and an opposite side of 10.24. To solve the first problem, to figure out what x is, the adjacent side, notice that x is adjacent to the 35 degrees angle, and 20 is the hypotenuse. We can use the cosine formula because we have the adjacent and the hypotenuse. We can say that the cosine of 35 equals x divided by 20. which also means that x equals 20 times the cosine of 35. Since the cosine of 35 degrees is 0.82, 20 times 0.82 is 16.38. To solve the second problem, we have the opposite side and we're looking for the adjacent side. Notice that y is adjacent to the 20-degree angle, and 10.24 is the opposite side. So we'll use the tangent formula of opposite over adjacent. The tangent of 20 degrees is 10.24 divided by y. The tangent of 20, as we can see in a calculator or look up, is 0.36. So 0.36 equals 10.24 divided by y, which is the same as 0.36 times y equals 10.24. If we divide each side by 0.36, we've got y equals 10.24 divided by 0.36, and so y equals approximately 28.44. Special angles. The angle theta for 30 degrees, 45 degrees, and 60 degrees is a special type of angle for which we can write down the exact value of the sine, cosine, and tangent for. Let's begin with a square of all sides whose are equal to 1. Note that the square has all equal angles of 90 degrees, so the diagonal side cuts the 90-degree angle in half and we get a 45-degree angle. The diagonal forms a right triangle with adjacent side 1, opposite side 1, and diagonal d. Thus we get the tangent of 45 degrees equals 1 divided by 1, which is 1. The sine of 45 degrees equals 1 divided by the hypotenuse, d in our case, and the cosine of 45 also equals 1 divided by d. 1 divided by the hypotenuse, again because sine is opposite over hypotenuse and cosine is adjacent over hypotenuse, and they're both 1 in this case. By the Pythagorean theorem, which we discussed back in Module 2, we know that 1 squared plus 1 squared equals d squared, which means that 2 equals d squared, which means that d equals the square root of 2. That tells us that the sine of 45 degrees and the cosine of 45 degrees are both 1 divided by the square root of 2. So if we need to compute sine or cosine of 45 degrees, we get the same answer as 1 divided by the square root of 2, which is approximately 0.707. Now let's consider an equilateral triangle. That is, a triangle all of whose sides have equal length, and we'll call them 2 units in all. Let h be the height, which is defined as the perpendicular distance from the top vertex to the base of the triangle. In this example, all of the angles of the equilateral triangle have to be equal, and the sum total of all angles in any triangle has to be 180 degrees, so it follows that all angles are 60 degrees each. When we drop the perpendicular from the top vertex to the base, and we call the length of the height h, we cut the vertex angle in half, and it becomes 30 degrees on each side. We also get 2 right triangles, with a hypotenuse of 2 in each case. Therefore, we can conclude that the sine of 30 degrees, which is the opposite over the hypotenuse as 1 over 2, the cosine of 30 degrees as the height divided by 2, the tangent of 30 degrees, which is opposite over adjacent, as 1 over the height. We also have the sine of 60 degrees if we look at the bottom angle, the base angle, the sine of 60 degrees being the height divided by 2, the cosine of 60 degrees being 1 over 2, that's the adjacent over the hypotenuse, and the tangent of 60 being h, or h over 1. It only remains to find out what h is. This can be done easily by using the Pythagorean theorem in the equilateral triangle. We can say 1 squared plus h squared equals 2 squared, which is 1 plus h squared equals 4, which means h squared equals 3, which means h is the square root of 3. Plugging everything back into what we just looked at, we can summarize in like this. For sine of 30 degrees is 1/2, sine of 60 degrees is the square root of 3 over 2, and the square root of sine of 45 degrees is 1 over the square root of 2. The cosine of 30 degrees is the square root of 3 over 2, the cosine of 60 degrees is 1 over 2, and the cosine of 45 degrees is 1 over the square root of 2. As far as tangent goes, the tangent of 30 degrees is 1 over the square root of 3, tangent of 60 degrees is the square root of 3, and the tangent of 45 degrees is 1. There are other methods for computing the exact sine, cosine, and tangent of angles by using various identities, but we can just leave it as this for now. An area formula. Suppose that we have a parallelogram, or a triangle, where we know the length of the sides and the angle between them, but don't know the height. We can find the area by applying this information and using the sine of the angle. In these examples, for both the parallelogram and the triangle, we have the sine of theta equals h over a, which also means that the height, or h, equals a times the sine of theta. Now, since the area of the parallelogram is base times height, we get that the area of the parallelogram is base times height, which is base times a times sine theta, which means ab times sine theta. As the area of a triangle is 1/2 the area of a parallelogram, we can get the triangle's formula as 1/2 of ab sine theta. Thus, to summarize, the area of the parallelogram can be computed by multiplying the two sides together and then multiplying it by the sine of the angle between the sides. The area of a triangle can be done the same way, just by multiplying that exact same formula by 1/2.